If you look back at the early days of the web, JavaScript had a very strict, very narrow job description. It lived entirely inside the web browser, responsible for basic front-end interactions, things like highlighting a button when you hover over it or submitting a form. But developers wanted a unified language. By the mid-1990s, they chased a concept called server.js, which meant pulling JavaScript out of the browser and running it on a backend server. Netscape actually tried this out with a tool called Livewire, but it never gained traction. The execution speeds were abysmal. The backend environment is brutal. A server has to juggle massive amounts of concurrent traffic and manage highly complex data routing. The original versions of JavaScript were simply too lightweight to survive that kind of workload. It became clear that tweaking the language wasn't going to be enough. For JavaScript to ever successfully cross over to the server side, its entire underlying architecture needed an absolute total overhaul. For years, backend programming was dominated by languages like PHP, Python, and Ruby. These operated on robust, multi-threaded server frameworks that were specifically built to handle heavy lifting. The way these traditional servers manage traffic is through a blocking model. Every time a new user visits the website, the server creates a brand new, isolated thread, a dedicated slice of memory and computing power assigned specifically to that one person. This chart shows multiple distinct processing lanes, representing those individual user threads. Notice what happens in the third lane. If that user requests a flow task, like reading a massive file from a hard drive, their specific thread freezes entirely until the job is done. Multiply that by thousands of concurrent users. As more and more threads get stuck waiting on data, the server's memory fills up. The physical hardware maxes out, creating a massive digital traffic jam. As internet traffic exploded in the 2000s, this model became increasingly expensive to maintain. Web developers desperately needed a way to manage concurrent traffic without crushing their underlying hardware. That solution finally arrived with Node.js. It took the old concept of server-side JavaScript and actually made it viable by snapping together two distinct, highly capable pieces of technology. The first piece was the V8 engine, which you can see highlighted here on this Chrome architecture slide. Google built V8 to compile JavaScript directly into highly optimized machine code, permanently solving the language's historical speed problem. The second piece was an open-source background library called libuv. If V8 provided the raw horsepower, libuv provided a radically different operational framework. Node.js bundled them together. The V8 engine allowed the JavaScript to run incredibly fast, while libuv supplied the structural architecture required to route millions of concurrent users without collapsing. The secret to that architecture is the event loop. Instead of spawning a heavy, dedicated thread for every single user, Node.js uses one single hyper-fast thread to constantly juggle all incoming traffic. This flowchart illustrates the difference perfectly. Think of traditional servers like a restaurant that hires a dedicated waiter for every single table. Node.js operates like a single, highly efficient fast food cashier, taking orders from a long line of people. When you ask the server to read a file, the main thread doesn't stand there waiting for the hard drive to spin up. It instantly offloads that heady task to libuv's background thread pool, leaving the single main thread immediately free to take the next user's request. Once the hard drive actually finds the file and the background task is finished, we hit callback time. The event loop grabs that completed data and pushes your original request right back to the front of the line, so the server can send you the file. Because the main thread never stops to wait for a slow process, it creates a continuously moving non-blocking system. By constantly routing traffic instead of waiting on it, that single thread can outperform hundreds of heavy traditional server threads. The elegance of this non-blocking system becomes incredibly obvious when you actually sit down to build a web server. This is a standard JavaScript file running on our local machine using Node. First, we import Node's HTTP module. Then we write a simple create server function that automatically fires every time a user makes a request. Inside that function, we define exactly what we want to send back to the user. We set the content type and then pass a simple text string saying, "Hello world" from the server. Finally, we tell our new server to actively listen for incoming traffic on a specific channel, like port 3000. You save the file, open your terminal, and simply type node server.js. In less than 10 lines of code, you have broken JavaScript out of the browser and stood up a fully functioning backend web server. Now, just because Node.js is incredibly efficient doesn't mean it should be used for everything. Relying entirely on a single thread creates a very specific operational profile. Node thrives in IO-heavy environments. If your application needs to constantly fetch information, talk to a database, or route messages between users, like in a REST API or a real-time multiplayer game, Node.js handles that traffic beautifully because it never has to analyze the data itself. But look what happens with a CPU-heavy task. If a user asks the server to render a complex video or run an intense mathematical algorithm, the central thread has to stop and do the math itself. That single cache is completely frozen, blocking every other user waiting in line. Because of this vulnerability, developers have to carefully audit exactly what kind of workload their application will demand before they commit to a backend architecture. Node.js has limits, but its impact is undeniable. It took a language built for clicking buttons and used it to rethink how we route web traffic, making the high-speed, real-time applications we use today the standard for the modern internet.